Okay, we're picking up here chapter 5, which we started, and we were talking about chemistry things here. We talked about atomic mass, I believe. And remember that the atomic mass that we do see on the periodic table there, which is the number on the bottom, can be represented as AMU per atom. AMU being an atomic mass unit. And they are, as we talked about, basically average atomic masses of all the naturally occurring isotopes for those particular elements. And we could calculate the atomic mass by taking the percent abundance of the first isotope times the atomic mass of that first isotope. We then would add it to the percentage of the second isotope times by its atomic mass of the second isotope. And then obviously if we had more, we would just kind of continue that pattern. We talked about after that a couple of sort of really conversion factors. It's a little bit more useful than AMU per atom. We started with Avogadro's number, and remember that Avogadro's number is 1 mole of anything will be 6.022 times 10 to the 23. Most of the time we will use these as atoms or molecules as the common units, but those units can change again depending on sort of what you're doing. It is really Avogadro's number here, our conversion factor to go from moles to atoms or molecules and backwards. Also a reminder, as we talked about a number of times, when we do see MOL, it is moles and not molecules, so do not get that confused. That also means that if there is no mention of atoms, molecules, or particles, or any of those type of things, you really don't need to use Avogadro's number. So don't use it where you're not supposed to. Speaking of on the periodic table here, a more useful unit for what we see on the periodic table is what is referred to as the molar mass. The molar mass has units of grams per mole, and the number represents how many grams there are, and it's always per 1 mole. So if we have one thing by itself, just an element, for example, we would look at the bottom number, and that would again give us, 55, for example, 85 grams per mole, which we could use as a conversion factor. If we had something that is a molecule that has multiple elements, again, we just basically add up the parts there from the periodic table. So that's 2 of the hydrogen's molar mass plus 1 of the oxygen's molar mass. And that gives us 18.02 grams per mole. So again, we always do molar mass based on just strictly the formula by itself. Again, regardless if we have it in an equation or anything like that, and there's a coefficient in front of it, it's just basically based off of just the one formula by itself. And that's why it's always per 1 mole. And molar mass is probably the sort of conversion that we use the most in chemistry. And that is going from grams basically to moles, or moles back to grams. And again, that's the molar mass from the periodic table. It's basically our conversion factor. It is really the moles that sort of tie both ends of that calculation together. So for example, atoms are molecules, and maybe you want to end up in grams. Again, it is that moles that sort of tie both of those together. Here using Avogadro's number, and here using the molar mass to go backward. Any questions on any of that stuff that we talked about last time? Yeah. Yeah, so moles is really the one that kind of ties them together. So if you have either of those units to start with, atoms or molecules, or you do grams, in order to get sort of to the other units, you got to kind of go through moles. And again, Avogadro's number is the one that'll take you from that atoms to moles, and then molar mass will take you the rest of the way, moles to grams, or vice versa, going in the opposite direction. But yeah, moles is really the one in the middle of both of those guys. Other questions? All right, so we did some examples, do a few more here just to make sure. How many atoms are there in 0.55 grams of potassium? We look at potassium on the periodic table, 3910, I hope so. Yeah. All right, so give us a couple minutes there, see what you come up with. All right, let's take a look here. So we're looking for how many atoms there are in 0.551 grams of potassium. So the key word here is atoms. So that does tell us that we should use Avogadro's number here somewhere in this problem. We're at grams. And again, we want to end up at atoms. So as we were just talking about earlier, really the one that sort of ties those together are the moles. So in this case, we want to go from grams to moles, which we hopefully know is our molar mass from the periodic table to do so. Once we're at moles, then we could pull out our Avogadro's number, basically to take it to the end of what we are looking for in this case. So we'll go get our potassium here. And as we talked about, and also a reminder, typically speaking, molar mass, 4 significant figures is what you grab off the periodic table to use in calculations and just in general when you calculate molar mass of anything. So this means that we got basically 39.10 grams per mole for potassium. And we're going to use that really as a conversion factor. So we got 0.551 grams of potassium. Setting up dimensional analysis way, we want to go opposite. So the grams are going to go on the bottom here, so they cancel. The moles of potassium will go up on top. If we stop our calculation right at this point, we are in moles of potassium, which is halfway there. We got to here. So now we need to kind of take it the rest of the way using our Avogadro's number, which again is our 1 mole is 6.022 times 10 to the 23. And in this case, it would be atoms. Here, if you did want to get an answer, you could. I probably, again, would not round too much until the end when you do the next step. But here, I'm just going to continue on with the calculation. So again, the nice thing about setting it up as dimensional analysis, I could clearly see moles are up on top, which I want to get rid of. So I should put moles on the bottom here. And that would mean Avogadro's number should go up on top. Remember, opposites cancel, right? So our moles cancel. And now we're going to multiply across and divide to make sure we use our exponent button. Clear our memory, apparently. Let's try that. 0.551 times 6.022 to 23. I do want to hit equals there at the top when I'm done and divide by 3910 and hit equals. And it looks like we will end up with 8.49 times 10 to the 21 atoms of potassium in this case. 3 significant figures based off of obviously the only number that's in that problem, which is 3. Yeah. Any questions on that one? Okay, so obviously grams per mole, molar mass really important. I think we're going to skip these couple of examples coming up as they're very similar to what we just did. So we'll take a look at some other types of examples here. So let's take a look at this problem here. Good look. Let's go back and look again. There we go. In this case, we want to know how many atoms of hydrogen or hydrogen atoms there are in 72.5 grams of C3H8NO. So clearly one of the keywords here, right, are atoms. So again, we're going to need to use Avogadro's number. But in this particular case, we are not interested in everything there. We're just interested in the hydrogen part of it. So we're not actually interested in the carbons or the oxygens in this particular case. So we do need a way in this calculation to go from really the whole thing to just the hydrogen, which is what we're interested in. And one way that you could do that, and sometimes you're asked to do that, and sometimes you'll need to do that in certain calculations, is to sort of relate each element to the entire thing in the compound or the formula, is you could actually use the formula itself as a conversion factor. So when we look at this formula here, these numbers on the bottom, and obviously if there is no number, it represents 1 in that case. These numbers here on the bottom do represent the moles of each of those elements that are present. And that means that actually from this formula here, we could actually write some conversion factors from it or qualities. We could say that for every 1 mole of the entire thing, I would get 3 moles of just carbon. And again, that would be the subscript that's on the bottom. And I could say for every 1 mole of the entire thing, I would get myself 8 moles of hydrogen. And I could also have a relationship in 1 mole of the entire thing. That would get me 1 mole of oxygen, which obviously is no number written right there. So we could actually use the formula itself as a conversion factor to go from the whole thing to just whatever element we're interested in. And obviously in this problem here, we are interested in hydrogen. So we would be interested in this relationship here. And that relationship is really a mole to mole relationship, which tells us for sure that we need to get our grams into moles so that everything cancels out. So we do need to go in this case from grams to moles of the whole thing. And then once we have moles of the whole thing, we need to use the actual formula here to go from moles of the whole thing to really just moles of hydrogen. And once we have moles of hydrogen, we need to go to atoms of hydrogen. And we have our normal things here to help us do that. We have our molar mass. We have our actual formula here to do that. And we have our Avogadro's number on the back end of the calculation to allow us to get to where we're looking for. So the first step is we do need to get the molar mass of this compound. And again, as we talked about, you basically just add up all the parts that you got going on there. So from the periodic table, carbon is 12.01. And again, that is the number that we see on the bottom. Just like for hydrogen, we see 1.008. And for our friend oxygen, we see 16, or G. Let's go with more of an O, I guess. All right, so to add up the molar mass of this, we have 3 times our 12.01 grams per mole for our carbon. We're going to add it to 8 times 1.008 grams per mole for our hydrogens. And we'll add it to 16 grams per mole for our lonely oxygen. And now we have 3 times 12.01 plus 8 times 1.008 and a 16. Looks like a 60.09 grams per mole. So now that we have the molar mass of our entire compound here, our C3H8O, we could start the calculation. We're going to start with our 72.5 grams of the entire thing. We're going to use the molar mass of the entire thing to take it from grams to moles. So that would be our 60.09 grams on the bottom. So they cancel. Moles of our entire thing here up on top. Grams cancel. That pretty much takes us to this step right there. At this point, we can now use the formula. Bless you. We can now use the formula to go from the whole thing to just hydrogen, which is ultimately where we want to end up. And obviously, we would use this highlighted relationship that we saw earlier. And we can use it as a conversion factor, basically. So we want to get rid of the entire thing. And we can see from our dimensional analysis here, it's up on top. So the entire thing would go on the bottom so that it cancels. And up on top would go 8 moles of hydrogen. That's going to cancel out the moles of the entire thing. And now progressing this way, I am now at moles of hydrogen, which is really good. Obviously, if I wanted moles of hydrogen, I get an answer and put a box on it. But I do want atoms in this case. So now we're going to go from moles to atoms. And again, that's going to be our Avogadro's number to do that. So once again, we want to go opposites to cancel. So moles want to go on the bottom here of hydrogen. And on top would be 6.022 times 10 to the 23. And these would be atoms of hydrogen, as we're just into hydrogen at this point. And that should get us to atoms of hydrogen we're looking for. We're going to multiply across the top there, 72.5 times 8 times Avogadro's number using our exponent button. We're going to hit equals and divide by 60.09. And we will get, looks like 5.81 times 10 to the 24 atoms of hydrogen. It's a lot of hydrogen atoms. Any question on that calculation? clearly, if we were interested in carbon or oxygen, we could do a similar calculation to figure out how many atoms of carbon or oxygen there was. The difference would be at this point, basically. We would just use the proper relationship for either carbon or oxygen, and everything else would really be the same in this conversion. So this is definitely something that you are sometimes asked to do, and something that we'll see in the calculation coming up that you do need to do in some cases, sort of have that relationship between sort of the whole compound and each of the elements or moles of each of the elements that are present. Any questions on that there? All right, so let's try a couple more here. What is the moles and how many molecules are there in 23.2 grams of ethanol? And once again, your periodic table, 12.01 for carbon, 1.008 for hydrogen, and oxygen, 16. All right, so see what you come up for both of those. While we're at it, why don't we add one more? How many? We'll do how many grams of carbon are there? In the same 23.2 grams. All right, so try all three of those, see what you come up with. Okay, let's take a look and see how we're doing here. So we want moles, molecules, and really just carbon by itself. So really the first two parts are sort of together. We do have grams, and we eventually want to get to molecules, and we do want to stop along the way there with moles. And again, this is our same sort of pathway. We're going to need the molar mass to do so, and we will need Avogadro's number in this case, since we are looking for molecules. So we'll start with the molar mass of this compound, and again, we're going to just add up it all from the periodic table here. So we got 2 carbons, each at 12.01. We got 6 hydrogens, each at 1.008 grams per mole. We also have, in this case, just 1 oxygen here at 16 grams per mole in this particular case. So we're just going to add it together. And if we do that, I want to say 4607, maybe, yeah, something like that. That was good. 4607 grams per mole is our molar mass of C2H6O. Again, we're going to use that as a conversion factor here. So we'll do the first one here, which is 23.2 grams of C2H6O. Again, opposites to cancel, so we need to put the grams on the bottom. Remember that when you do molar mass, the grams always stays with the number always stays with the grams, and it's always per 1 mole there up on top in this particular case. The grams will cancel. So since we do want an answer here, we'll take 23.2 and divide it by 46.07, and that will get us 0.504 moles of our C2H6O. Any questions on that so far? That gets us again up to here in terms of our pathway. So now we can use Avogadro's number there to take it the rest of the way. I'm going to write the rounded number because we did want it as an answer here, but I'm going to actually on my calculator just continue on with the whole number that I got on my calculator. And at this point, we want to take our moles to molecules, which is our Avogadro's number. And we do want moles on the bottom so that they cancel. And up on top would go Avogadro's number. Here they would be molecules, as we're dealing with a molecule in this case. The moles will cancel. And again, I'm using the whole number, not the rounded number, 6.022 to the 23, and gives us roughly here 3.03 times 10 to the 23 molecules of C2H6O. Any question on either of those calculations there? Now, looking at the last one down here, we're interested in not the whole thing, but we are interested in just the carbon part. So this is where, again, we could use the formula to help us out. So from the formula here, we see that for every 1 mole of the entire thing, how many moles of carbon do I get? I get, not everybody at once, I would get 2 moles of carbon. Good answer, because that's a 2 right there. Yeah. So we do get 2 moles of carbon. I should write carbon, would be even better. There we go. And we could use that obviously as a conversion factor to go from the whole thing to just carbon, which is what we're interested in this case. And we're going to shortcut it because frankly, we have the answer right there for the moles of the whole thing. So no sense redoing the calculation. So again, I'm just going to pick it up with that number, which is our moles of our entire thing. And obviously to get there, you would do the first calculation again. And we're going to use the formula to go from the whole thing. So we want the whole thing on the bottom. And we want just the moles of carbon on top, which is 2 moles of carbon. So using the formula here, that's going to get rid of the whole thing, leave us with carbons. At this point, and once again, if I did want just moles of carbon, I could get the answer and I would be done. But I actually want grams of carbon, which means I need to multiply this by the molar mass of just carbon at this point, right? So we do not want to use the molar mass of the entire thing because we have now just transitioned over to just carbon at this point. And carbon, as we can see from the periodic table here, is 1201. So we'll use that as our last step. Opposites here, moles of carbon on the bottom, 12.01 grams of just carbon up on top. And in this case, we'll go here with the rounded number, 0.504 times 2 times 12.01, going to give us 12.1 grams of carbon in this particular compound. Yeah, about 50% carbon, so that's about right. Yes. Any questions on any of those calculations there? Your silence is reassuring, just so you know. All right, so let's try one more here just to reassure me one more time because it's caffeine. Maybe it'll keep you up. All right, so we're looking for how many grams there are in 1 molecule of, sorry, how many grams are there in 1 molecule of caffeine? That's what I'm trying to spit out there. All right, so some numbers again that we've been using still haven't changed. So we'll pop them up here anyways. We'll do our nitrogen and our oxygen. All right, so in this case, we're just looking for the grams in 1 molecule of caffeine. Look here. So once again, the keyword is molecules, tells us Avogadro's numbers involved. We want to end up at grams. So once again, we got molecules, we got to get to grams, and our moles are in the middle there. So we're going to first Avogadro number it, and then we're going to molar mass it, and then we will be out of stuff to do to it. So since we do need the molar mass at some point in this calculation, I'm going to calculate it up front here. So just going to add up all the parts here. So that's going to be 8 times our carbon's molar mass from the periodic table, plus 10 times our hydrogen's molar mass from the periodic table, plus we got there 4 times our nitrogen's molar mass. And lastly, 2 times our oxygen's molar mass. Good thing there's no more letters. I feel like I'm out of room there. We add all that together, $196 maybe, $194. 194.2 grams per mole is our molar mass. Any questions on getting the molar mass there? Again, obviously it comes from the periodic table and it's the bottom number there underneath the element. All right, so we'll start with our 1 molecule of caffeine. This big formula and 402. Just draw a cup of coffee instead. All right, so we're gonna use our Avogadro's number. In this case, we actually want Avogadro's number on the bottom so that the molecules cancel each other out. So 6.022 times 10 to 23 molecules on the bottom per mole of our caffeine up on top. At this point, the molecules of caffeine will cancel out. I'm in moles, which takes me basically to here. So what's left is, again, using our molar mass. So we just calculated there to go the rest of the way. And dimensional analysis wise, we see moles on top, which means on the bottom should go moles of our caffeine. And up on top should go 194.2 grams. The moles will cancel. That will give us grams. So basically 194.2, I think. Go divided by Avogadro's number, basically. Not too bad. And it looks like we will end up with, I'll come down here, 3.225 times 10 to the minus 22 grams of caffeine in this case. And in this case, to answer the question, we went 4 significant figures really based off of the molar mass, because if we had one molecule, that'd be kind of like something you would just count, right? So more of an exact number. So you really could give it to as many significant figures as you want at the end of this particular calculation. So I just went with the molar mass for significant figures in this particular case. Any questions on obviously converting grams, moles, grams? Need to know how to do that for sure. The occasional throwing in of Avogadro's number, not so much more used than maybe in this chapter, but definitely grams, moles, we use a lot. Any questions on any of that there? All right, we will lay it up there for now.